Okay, so today we're really diving into some fascinating stuff, topographic indices.
Mm-hmm.
You shared some really cool material on Thorne's Compound Topographic Index, we call it CTI,
Great.
and then Bevan and Kirkby's Topographic Wetness Index,
Mm.
TWI.
Yeah,
And our mission here is to try to help everyone listening understand
absolutely.
how these indices can actually help us understand how the shape of the land, the topography,
Right.
really dictates how water moves and then how that leads to erosion.
Yeah.
Um, this might sound a little technical at first, but,
Sure.
it actually has some really surprising and practical real-world implications for,
Yeah.
just how we understand our landscapes.
Oh, yeah, absolutely. And one of the first things that I think is important to kind of get out of the way right away
Okay.
is this acronym, CTI. You pointed this out earlier. It can actually refer to
Yeah.
two different things. So let's make sure we untangle that little problem right up front.
Exactly, yeah. First up, we're going to talk about Thorne's CTI,
Okay.
which was developed in 1986.
All right.
So, okay, let's unpack this a little bit. What Thorne's CTI was really trying to do was to predict the formation of something called ephemeral gullies.
Mm-hmm.
Now, you might
Huh.
be asking, what's an ephemeral gully? Well, these are really just small, but they can be very damaging erosion channels,
Right.
particularly in agricultural fields. So you can kind of think of it as like if you have a big rain event,
Yeah.
where does that runoff start to really carve little pathways, little channels into the landscape?
And the formula for this, Thorne CTI, is
Okay.
now A, in this case, is the upstream drainage area.
Okay.
So all the area uphill that contributes water to this point that we're looking at. S is the local slope.
All right.
So obviously steeper ground is going to mean that water flows faster.
Sure.
And then PLA and C is the planform curvature, which a positive value means that the flow is converging.
Gotcha.
So think of like water funneling into a point, which increases the risk of erosion.
So it's really trying to identify those areas where the water comes together
Exactly.
on a slope with a lot of force.
Exactly. Converges with force. Yeah, that's a great way to put it. And the output, what's interesting about this? It actually has units of length.
Okay.
And it represents this idea of specific stream power. So it really is trying to get at, how much force that water has.
Yeah, yeah.
And so the idea is that if that power exceeds the soil's resistance, that's when you get a gully forming.
That makes sense. And so I know that researchers will often look for a certain critical CTI value.
Yes, a threshold, that's
A
right.
threshold, yeah, to say, okay, this is where,
Which is where it's going to happen.
yeah, this is where it's going to start eroding. Of
Exactly.
course, how accurate this is depends on, how good is the topographic data we have.
You got it.
Right.
Yeah. Yeah.
Okay, now let's shift gears and talk about Bevan and Kirkby's Topographic Wetness Index, TWI, from way back in 1979.
All right.
Now, this was developed as part of their top model, which was really trying to predict runoff.
Mm-hmm.
So the goal here with the TWI was to try to figure out how topography, how it influences soil saturation. So basically, where does water,
Where does it want to
Yeah.
out? Yeah, where does it like to collect?
where does it want to pull up?
Yeah.
And the formula here is a little different. It's like, imagine the upslope area, but per unit of contour length. So it's kind of how much is accumulating along the slope.
Okay.
And then Ln is our local slope angle.
Oh, right.
So the tangent of that is telling us how easily water can drain away.
So it's looking at kind of the balance between the inflow and how
Exactly.
easily it can drain.
That's exactly right.
Yeah.
So what it's really getting at is where the topography kind of naturally wants to collect and retain water based on that balance.
Okay, gotcha.
So a high TWI means it's more likely to be wet. A low TWI, it's more likely to drain quickly.
All right, and the output for this one is dimensionless, right?
That's right.
It doesn't have any units.
It's just a number. That's right.
Okay, cool.
So let's kind of summarize some of these key differences.
Yeah.
So Thorne CTI,
Okay.
you're multiplying the components. And one of those components, importantly, is that planform curvature.
Right.
And the output actually has units of length.
Mm-hmm.
TWI, on the other hand, uses division, and a logarithm doesn't have curvature in its original form.
Right.
And it's dimensionless.
That's right.
And, these mathematical differences kind of really show up in how they're applied.
Absolutely.
So Thorne's CTI, because it's got that curvature in there,
Yeah.
is really good at predicting gully erosion.
Especially in agriculture, yeah.
Yeah, particularly in agricultural settings. You mentioned that really interesting study in Navarre, Spain,
Mm-hmm.
where they actually used it to successfully predict where these gullies were going to form.
Yeah, pretty cool.
Yeah, that was really cool. And then TWI on the other hand.
So that one's really good at predicting soil saturation and runoff, so super important for hydrology. But what's interesting is it also gets used in ecology. Like if you want to understand vegetation patterns, cause obviously that's influenced by soil moisture.
Oh, yeah, that makes sense.
And even in flood risk assessment, where's the water going to want to accumulate?
Yeah, that's fascinating, and it all comes down to the shape of the land.
I know. It's amazing how much the topography really drives all these processes. And,
Absolutely.
we've got to talk about this CTI as TWI confusion.
Yeah, this was kind of tripping me up.
Yeah, no, it's a real problem. So a lot of researchers, they use CTI, but they actually mean TWI. So they mean that L at tan formula.
And I'm guessing this is probably because both of them are trying to look at...
They both relate topography to water, yeah. It's natural that it would happen.
But this is where it's so important to pay attention.
Absolutely.
You have to check the formula.
You got it.
Check the context.
Yeah.
If someone's talking about gully erosion, you can bet they're talking about Thorne's CTI.
Right.
But if you're talking about hydrology or ecology, it might be TWI.
Exactly.
All right, so to recap, what do we got? Thorne's CTI, that's erosion potential, and it uses curvature.
That's right.
Bevan and Kirkby's TWI, that's wetness potential, and in its original form, it doesn't use curvature.
Exactly.
So listeners, the big takeaway here for you is to always be clear about which index you're talking about.
Yeah, definitely.
Or which index is being used in a particular study.
Absolutely. What's amazing to me here is that these, they seem like kind of abstract indices, right? You're just looking at the shape of the land.
Yeah.
But they have such practical implications for how we manage our landscapes, like preventing soil loss on farms, understanding flood risks, even predicting where certain plants might thrive.
Yeah, it's amazing.
It is.
So as a final thought for our listeners, beyond just these indices, think about this. What other hidden ways might the shape of our world, which seems so static, actually have really dynamic consequences that we're only just beginning to understand?
Fascinating question to think about.
Yeah, thanks for this deep dive. It was really enlightening.
My pleasure.
Yeah.
Glad we could untangle it together.
Yeah, for sure.
Yeah.
Okay.